Guys, we are about to discuss question number 48 from Nootan ISC Physics. The question says that we have been given a parallel plate capacitor. When there is no dielectric between the plates, the capacitance of that particular capacitor happens to be 0.5 microfarad. Then we insert two dielectrics in between the plates, one having a dielectric constant of 2, another having a dielectric constant of 3. And then we form two different capacitors depending upon the manner in which we have inserted the dielectric. Now, if you see in this first figure, the dielectric has been inserted in such a manner that it occupies the entire space between the two plates, but occupies only just half the area. So the area occupied by the dielectric in the figure number 1 occupies the entire space between the two plates, but it just acquires half the area of the plate. So it just acquires half the area of the plate, but it requires the entire distance. So this is the first orientation in the manner in which we have inserted the dielectric. Now, if you look into the second figure, you will find the capacitor, the dielectric occupies the entire area of the plate, but it occupies only half the distance between the two plates. So this occupies half the distance, this occupies half the distance. So there are two different configuration of capacitors being formed. The question asks us to find out the capacitance, the ratio of the capacitance of capacitor 1 orientation with the ratio with the capacitance 2 of the figure 2 orientation. So friend, this is the question which we are about to discuss from Nootan ISC Physics. If you have not watched my earlier video on capacitance of a partially filled capacitor, I will advise you to first go and watch that particular video before watching the solution of this particular numerical problem. That will enhance your learning and understanding of this particular question. Friends, if you like this video, you might consider liking and subscribing to my channel and sharing this video with your friends and colleagues. So let's begin with the solution of this particular problem. So friend, there is a capacitor, a parallel plate capacitor. So if we have been given a parallel plate capacitor like this, having capacitance C or simply say CA, where A happens to be the area of the plates and D happens to be the distance between the two plates of the capacitor. Then you know the capacity and the space in between between the two plates is filled completely with the help of air. Then you already know the capacitance of such air-filled capacitor might be written as epsilon naught A by D. So this is the expression that you are already aware of it in your classes, in your theory classes. You might have been told how to derive this particular formula or particular expression, and you might have learned that. Now, what is happening in this particular question? The space between these two plates is filled by two different dielectrics. Now, there are two different orientation in which the space between these two plates are being filled. So let me draw the figure the way they have depicted. So this is two parallel plates, and the space between these two parallel plates is filled by two different dielectrics. So what I'm going to do, I'm going to fill this space between the two plates by two different dielectrics. So this is one dielectric, and then I've got a second dielectric which is filling the remaining space. Okay, just ignore the space that has been left. Let me redraw the figure. So this is the situation. The entire space is being filled with the help of two different dielectric, one having a dielectric constant of K1, another having a dielectric constant of K2. So you can visualize this combination of capacitor as, I'm redrawing this figure. So this is one capacitance, okay, having the space completely filled with dielectric K1. So you can see the distance between the two plates, these are the two plates, is still D, and the area of the plates is half that of the original. The space, the distance between the two plates is still D, but the area of the plates have been reduced to just the half what it was over here. Now, at the same time, I'm having another dielectric material. Let's call that dielectric material to be K2, which occupies the remaining half of the area of the plates. So what is happening in this case? It occupies the remaining half of the area between the two plates. So in this case, this is a K2 dielectric, and it occupies half the area, friends. Let's redraw this. So this is another one. These are the two plates, the black color one. Okay. So it occupies, now this material occupies the entire space, entire distance between the two plates, but just occupies half the area. Now what is happening, if you refer to the figure, these two upper plates are joined with each other, while these two lower plates are also joined with each other. You can see these two plates are having the connection. Now what I'm doing, just I have separated this figure for you to have a better understanding. So this space between these two plates is joined by another. So upper plate is joined by, the two upper plates of both the capacitor are joined one with each other, whereas the bottom plates of the plates are also joined with one another. So what you can do, you can think about this as one capacitor. Let me call this as C dash, and the capacitance of the C dash capacitor will be K epsilon naught A by D. Okay, instead of A, it will be A by 2 by D, where K happens to be the dielectric constant of the medium in between the two plates. So here the dielectric constant in between the two plates happens to be K1 epsilon naught. The area of the plates is A by 2, and the distance between the two plates is D. Now similarly, in this case, you can consider as another dielectric, and the capacitance of this capacitor will be C double dash. The space is now filled by a dielectric of medium dielectric constants K2 to K2 epsilon naught. The area of the plate is now A by 2 divided by D. And see friends, both the dielectrics are now connected in parallel. How can I decide they are connected in parallel? You can see their upper ends of the plates are joined together, their downward plates are joined together. So when both the when one end of the same plates, left end is joined together or right end is joined together, then the combination is called as parallel combination. Series and parallel combination you might have studied earlier. What happens in parallel combination? The left plates of the capacitor are joined together at one point, while the right plate of both the capacitors are joined together at one point. तो अगर बच्चों इस तरह से capacitors की plate आपस में जुड़ जाती हैं, तो हम इस combination of capacitors को कहते थे they are connected in parallel. तो यहाँ पर भी you can see that both the upper ends of the plates, this is the upper end, this is also the upper end of the 1 capacitors. This is the C1 C dash capacitors upper end, and this is a C double dash capacitors upper plate. Both the upper plates of the capacitors are connected together, and here you can see this is the downward plate, this is also the down plates, and both the down plates are connected together. So जब up plates और down plates आपस में connect हो गए, तो ये दोनों capacitors are now connected in parallel. So the net capacitance of such capacitor can be easily found at C net is equals to this. Since they are connected in parallel, so what I'm going to do, I'm going to apply the formula of the parallel combination, that is C1 plus C2. Now referring to this particular combination, so C net will be C dash plus C double dash. Now let's say what is C dash over here? The C dash over here happens to be K1 epsilon naught A by 2D. And what is C2? That happens to be K2 epsilon naught A by 2D. And on rearranging these terms, you will find that C net of the C1 configuration, this is the way we have got. The C1 is the C net of this. Epsilon naught A by 2D is common in both the things, will be equal to K1 plus K2. Now friend, as per the question, the air-filled capacitor has got a capacitance of 0.5 microfarad. So CA happens to be 0.5 microfarad, friends. My mistake earlier. So the capacitance of air-filled capacitor is 0.5 microfarad as per the question. So what I'm going to do, I've got the value of epsilon naught A by D being equal to 0.5 microfarad. So while I'm going to substitute it over here, the C1 will be equal to, now remember this as a formula, if the space between the two plates is completely occupied by two different capacitors of equal size, the capacitance happens to be epsilon naught A by 2D K1 plus K2, where K1 is the dielectric constant of one capacitor and K2 happens to be the dielectric constant of another capacitor. So friend, this is going to be epsilon naught A by D, epsilon naught A by D into 1 by 2 K1 plus K2. Let's substitute the values that has been given as per the question. Epsilon naught A by D is 0.5 into 1 by 2. The K1 happens to be 2 and K2 happens to be 3. Now refer to the problem. They have already stated K1 being equal to 2 and K2 being equal to 3. So you can see over here they have mentioned K1 as 2 and K1 being equal to 3. So that is the way. That's the way to find out the net capacitance C1 of this, and this happens to be 0.5 divided by 2 into 3 plus 2 is 5, that is 2.5 divided by 2, and that comes out to be 1.25 microfarad. And so this net capacitance comes out to be 1.25 microfarad. So probably you might have understood how to find the net capacitance of the orientation 1 when the dielectric has been inserted in such a manner that it occupies the entire space but half of the area of the plates. Okay, now in the second orientation that we have been given, what is happening, the dielectric does not occupy the entire space, the dielectric does not occupy the entire space, entire area of the plates, but it requires, in the second orientation, the dielectric does not occupy the entire distance between the two plates. This distance has not been occupied completely by the dielectric, but it occupies just half of the distance. So up in this particular orientation where you are finding the dielectric to occupy just half the distance between the two plates, what capacitance we are going to obtain for second orientation? Let's do that problem. So the question says the dielectric now occupies just half the area. So this is one dielectric. Let me call the dielectric of this material as K1 by 2. And then I have got the second dielectric K2. This is the K2. The dielectric constant of K2 happens to be 3. Now these two dielectrics have occupied half of the distance between the two plates. This is one plate, this is another plate. The dielectric now occupies half of the distance. So what I'm going to do, the same figure can be thought of as this one dielectric. So this is one. This becomes my one capacitor. The entire space of this capacitor is filled by a medium C having dielectric constant K1. So the capacitance of this capacitor can now be written as C dash. Yes, C1 is equals to K1 epsilon naught. That's the dielectric constant of the medium. Now the area is completely occupied by this dielectric, that is the A area is completely occupied by the dielectric, but the distance now that it occupies is only d by 2. That becomes the dielectric, that becomes the capacitance of this capacitor C1. And what is happening? It is connected side by side with another capacitor whose entire space, whose entire area is filled with dielectric constant K2. Okay, so this is one plate of that capacitor. This is another plate. The space is completely filled now. This entire space is completely filled with dielectric K2. Okay, dielectric K2. So the capacitance of this capacitor C2 will be K2 epsilon naught. The entire area is filled with this dielectric, but the space, the distance that it occupies happens to be only d by 2. And you can now see both these dielectrics are connected side by side, one after the another. So here what you are finding, the capacitors, this is one capacitor C1 which is connected with another capacitor C2 in series, one after the other. Here what you were observing, the two capacitors were connected, but their plates, their upper plates or their downwards plates were connected together. Here you find the upside of the plate is not connected with the upside of the plate. You are finding their one plate being commonly connected. If their one plate is commonly connected, then such combination is called as series combination. So in this situation, these two capacitors are connected in series, and probably you are well aware of the series formula, 1 upon CS is equals to 1 upon C1 plus 1 upon C2. This is the formula that you are going to apply. 1 upon CS is equals to 1 upon C1 plus 1 upon C2. So what is 1 upon CS? 1 upon CS. Here 1 upon C1, what is that? that happens to be, we are reciprocating that, it will become d by 2 times of k1 epsilon naught a, and 1 upon c2, when I'm going to reciprocate it, will become d by 2 k2 epsilon naught a. Rearranging these terms, you can find it to be written as d by 2 k1 epsilon naught a plus d by 2 k2 epsilon naught a. Now 1 upon cs. Now what I'm going to do, whatsoever is common, I'm going to take it outside, so you can see d by 2 epsilon naught a is common in both the things. D by 2 epsilon naught a. What I'm left with, 1 by k1 plus 1 by k2, and this happens to be 1 by cs, or the same can be reversed, reciprocated to get the formula for cs, and that happens to be epsilon naught a by 2d. This gets reciprocated and this entire expression will get reciprocated, and it will become 1 by k1 plus 1 by k2. Or what you can do, you can also rewrite this expression. If you're not able, let me just run it up. What you can do, let me rearrange this thing. This is 1 by cs d by 2 epsilon naught a. What I'm going to do, I'm going to solve this bracketed term. Here it is k1 k2 upon k1 plus k2. What I've done, I've solved this bracketed term, and after solving this, I will get 1 upon cs as d times of k1 plus k2 upon 2 epsilon naught a k1 k2. Therefore, cs comes out to be, on reciprocating it, 2 epsilon naught a k1 k2 upon d k1 plus k2. So this is the expression of the second orientation of the capacitor, that is C22. So 2, what is epsilon naught a by d? If you refer to the earlier discussion, it is earlier part of our discussion, this epsilon naught a by d has got a value of 0.5. So that comes out to be 0.5 over here. K1 into K2 is 2 into 3 upon K1 plus K2 is 2 plus 3, and this 2 plus 3 will make it 5. So this becomes 2 into 0.5 into 3 2s are 6 upon 5. This 5 and this 5 cancels out. This point gets written over here. 6 2s are 12. So the expression comes out to be 1.2 microfarad. So the net capacitance of the second orientation of the capacitance happens to be 1.2 microfarad. Now the question asks us to find the ratio of C1 orientation with C2. So C1 is to C2 is equals to 1.25 is to 1.2. So this is the expected answer. C1 is to C2 happens to be 1.25 is to 1.2. And in fraction, if you want to write it down, this will come out to be 25 is to 24. C1 upon C2, if you want to simplify it out, so this is 1.25 upon 1.2. This point goes, you can put over 0, 25. So you can cut it by 5, 5 25s are, and 5 24s are. So the correct answer comes out to be, either you can write down 1.25 is to 1.2, or you can also write it as C1 upon C2 as 25 by 24. And that should be the answer given in your book. So hope friends that you all have understood the manner in which this particular numerical was supposed to be solved.